what is an unstructured mesh? Okay. The only thing you have to worry about, or the only definition that I care about, is it has no predetermined IJK ordering or numbering pattern. That's all. Okay. The mesh that you've been using to solve your Poisson equation, that can be treated as an unstructured mesh. It's just a special case of an unstructured mesh where the numbering is ordered. But if you develop an unstructured solver for that, the numbering could be anything. It doesn't rely on the fact that, it's IJK ordered. The control volumes, and because it doesn't rely on IJK ordering, you're not stuck into this framework of having to match opposite faces, okay, or opposite edges. And therefore, the control volumes can be of arbitrary shape. It could be a mixture of triangles, quadrilaterals, or arbitrary polygons in 2D, tetrahedrons, hexahedrons, prisms, pyramids, etc. in 3D. Okay, a structured mesh is just a special type of an unstructured mesh in which the numbering follows a certain pattern. Okay, so if you look at modern mesh generators, they have both structured mesh generation capability and unstructured mesh generation capability. Okay. Now, after the mesh has been generated, the procedure used to generate these two types of meshes are completely different. Okay, because one requires, opposite face matching and all that. So, but once you generate the mesh, then it will ask you, most mesh generators, okay, what PDE solver do you want to use? Okay, so for example, ISM-CFD, which is one of the mesh generators used with ANSYS, they have a choice that, okay, what final solver are you going to use? So it will output it in that format. So for example, if you output it for Fluent, it knows that Fluent has an unstructured solver, so it will output it in unstructured format, and then once you read it into Fluent, it may look like a nice structured mesh, but the internal calculations are all for an unstructured mesh. Okay, so that's what's going on in the background. So a PDE solver written for an unstructured mesh will automatically be able to handle any structured mesh. Okay, it's not that whatever work we have done before is wasted. So what do you have to do to then develop an unstructured mesh? Okay, so let's start with the very basics. So the first thing is geometry and mesh processing. Okay, the cells are not numbered in any particular order. So the first thing you have to do is you have to number them, and then you have to know the relationship between the numbers. Okay, so first thing is the mesh generator will automatically number each cell using its own internal algorithm. Remember when I taught you this simple Cartesian 2D mesh, I gave you sort of this numbering pattern with a formula saying k is equal to j minus 1 times n plus I. That's a numbering pattern I cooked up. I could have said, well, I'm just going to draw a random number between 0 and 1. Wherever that random number falls, that's going to be the next cell number. Okay, could have done that, numbered them arbitrarily or randomly. Okay, that would just still maintain that nice Cartesian mesh, but it would become an unstructured mesh. Okay, same thing with face numbering. So it will use an internal algorithm of its own and come up with a unique number for each face. Okay, so here is just a simple example of some numbers. Okay, so of course this is a triangular mesh, but it could be applicable to a Cartesian rectangular mesh too. So here are the cell center numbers in blue, and then the red numbers are showing you the face numbers, okay, and the green numbers are showing you the vertex numbers. Okay, the vertex numbers are what people typically refer to, or finite element people refer to, as nodes. Those are the ones that they use for their computations. Okay, whereas we in finite volume, we are more interested in these guys. That's where we store our information, the cell centers. Okay. So the mesh generator will print out all these, or it has the ability to print out. So if you are trying to develop an unstructured code, and let's say you put your money on one mesh generator, you have to have some sort of mechanism where you can extract all this information from the mesh generator. Okay, most mesh generators have certain APIs that will allow you to print out this kind of information into a file. All right, so things like what are the total number of cells in the computational domain, what are the total number of faces, total number of nodes, coordinates of all cell centers, coordinates of all face centers, coordinates of all vertices or nodes. Okay, so pretty straightforward to understand. So those APIs may be in the form of user-defined functions, which you call inside some program, or which the mesh generator will let you hook on to the mesh generator as a macro, and it will print out those kinds of information into a file. Okay, so that's actually the hard work, or it's what should I say, not very interesting to do, but it's something you have to do if you are to generate a PD, or if you are to write a PDE solver for an unstructured mesh. Okay. It will also produce the following information: total number of faces of each cell. So for example, this is called N, let's say we call that N face with a cell index. So for example, N face of cell number 32 is 3. That's simply telling you that cell number 32 has 3 faces. Okay. Total number of nodes of each face. So for example, here it will be N node of 2 is equal to 2, because this face here, face number 2, has 2 vertices. Okay. In addition to the global numbering, each cell will also have a local numbering, 1, 2, 3. So for example, 1, 2, 3 are the 3 faces of that cell. Okay, that's local numbering. The global numbers are 2, 99, and 41. Okay. So in an unstructured mesh, since these cells are not numbered in any pattern, you have to store the so-called connectivity. Okay. This connectivity comes in different forms. You have cell-to-face connectivity, face-to-cell connectivity, face-to-node connectivity, and so on. There are other forms too. We'll talk about those. Okay. So this connectivity information must come from the mesh generator. No one else can tell you that. Okay. So here is an example, cell-to-face connectivity. So what this is saying is, so I've created an integer array. So one of the very important things of writing an unstructured code is coming up with or planning out your data structure. How many integer arrays do I need? How many real arrays do I need? What sort of shapes should they have? Should they be 2D? Should they be 2D? What sort of length should they have? Should they be numbered, number of cells, number of faces, and so on? Okay, so those decisions you need to make a priori, plan it out, and then write your code. So for example, if I call my cell-to-face connectivity as link from cell to face, that's what this means. Okay, so it has 2 indices, cell index and a local face index. So here's an example. So I'm saying link from cell to face of cell number 32, that's this guy, face number 1, this is the local face number. Okay, and this stores the global face number. So local face number 1 becomes global face number 2. So it's storing that number. Okay, so if I run a loop over the total number of faces of that cell, I go 1, 2, 3, and from 1, 2, 3 I can get the global face indices, and the global face indices can then give me things like areas, surface normals. Okay, so from the cell number I go to the global face number using that connectivity information, and then from the global face number I can get all other kinds of information. Okay, everybody understand that, what this is doing here? Then you have face to cell. Face to cell is the opposite. So here we are saying face number 2, there can be only two cells next to a face. There is no other way. Okay, if I have a face, there will be 2 control volumes adjacent to it, whether it's 2D or 3D. All right, and those 2 will have 2 numbers, 1 and 2, and in this case they're 12 and 32. So this one I'm calling cell number 1, this one I'm calling cell number 2, adjacent to face number 2. Okay. So these local cell indices 1 and 2 are arbitrarily set by the mesh generator. However, it is customary to use these indices to determine the direction of the surface normal, and the surface normal is stored in a manner that it always goes from local cell 1 to local cell 2. Okay. So in this case, that pink arrow denotes the surface normal. That's how it's going to be stored. Okay. Going from cell 1, which is 12, to cell 2, which is 32. Okay, so it's going from 12 to 32. If my cell number 1 was 32 and my cell number 2 was 12, then it would be going the other way around. Okay. Everybody follow that? All right. Let's talk a little bit about boundaries. So here is I'm showing a boundary face, which is face number 2. Okay. Then what happens is there is no cell here, right here. So when I do this connectivity, cell number 1 and 2, cell number 2, customarily what happens is the mesh generator will return the same number, 32 for both. Okay. And that information is often used to figure out if it's a boundary face or not. So you get the cell numbers next to a face, and if those two are equal, cell 1 and cell 2, then you know it's a boundary face. Okay. Face to node connectivity, same idea. So here, for example, I'm using face number 2 as an example. The first node is 29, that's this guy, and the second node is 56, that's this guy. So the mesh generator will also typically output total number of boundary faces and whether a face is a boundary face or not with a flag 0 or 1. So for example, it will store an integer array called B face, which will be either 0 or 1. Okay, if it's 1, then it's a boundary face. If it's 0, it's an interior face. All right. Same thing for nodes. Whether that node resides on a boundary or not, it stores a flag to indicate that. Okay. Now, storage of surface normal, I already talked about. So this is a real number of size n faces times 3. Okay. This is not an integer anymore because we have to store the 3 components. So the surface normal, you give it a face index and then components 1, 2, and 3 stores the 3 components. If it's a 2D mesh, it will just store 2. Okay. It's pointed from cell 1 to cell 2. So some surface normals may be pointing inwards, some may be pointing outwards, depending on what the mesh generator has assigned cells 1 and 2. Okay. So, but we need to know that a priori to be able to do our calculations. We must know, if I'm at a cell, I must know which way my surface normals are pointed at each face. It's pointed inward or outward. Okay. So how do we determine that? So here is how you determine that. Okay. So suppose I'm at a given cell, IC equal to 1, let's say I start with. So this is, well, in this case, let's say I'm looking at cell number 32. Okay. So what I do is from 32, so I'm looping over, so from 32 I'm getting the face number of the first face. Okay. That may be that one. Okay. From the face number, I calculate, okay, what is cell number 1 of that face? Is it this one or that one? Okay. That I'm calling IC1, the cell number 1 from that face. If that number that I get is equal to the cell from which I approached that face, then that means that the surface normal is already out, pointing outward. Okay, because what happens is then IC becomes equal to IC1. In other words, whatever cell number you started with is the same as what this guy returns. Okay? So then the surface normal is already pointing outwards. Otherwise, you flip the surface normal and assign a negative sign to it. Okay? So this is the sign of the surface normal that I'm storing. Notice that this integer has the cell number as well as the local face number, okay, or the global face number, because the surface normal that I'm looking at is from the perspective of the individual cells. Okay, it's not a unique direction. It's how I look at which cell am I in. If I'm looking at it from here, I see this surface normal coming in, but if I'm looking at it from the next cell, I see that surface normal going out. Okay, so therefore this sign is stored in such a way that it is cell based. Okay, cell and face based. So you're giving it the cell number as well as the face number of that cell, and from that it has either a +1 or a -1. +1 means it's already pointing out, -1 means it's pointing inwards, and so I'm flipping the sign in a sense. Okay, and then you repeat that for all the other faces. So that's the algorithm one would use to store the sign of the surface normal from the perspective of each cell. Okay, now how do you use that? So suppose I ask you to calculate, okay, what is the net outgoing flux from a cell? So you've post-processed your data, you've calculated all the fluxes, the vectors, the flux vectors at each face. Imagine that it's mass flux. And I say, tell me in cell number 32, what is the net outgoing flux mass from that cell? Okay? Or I want you to tell me, is it going in, is it going out, and what's the value? That's a typical question one would pose. Okay? So, in other words, this is what you need to calculate. So how do I code that? This is the code for it. Okay? So what I'm doing is, I'm taking the x component of the flux at face f. Notice that f is going from 1 to 3. Okay, I'm taking the x component of the flux. I'm dotting it with the surface normal. Okay, so that means flux x times the x component, flux y times the y component, flux z times the z component. Those are the three components of the surface normal. So basically, I'm doing jx times nx plus jy times ny plus jz times nz. That's what I'm calculating. That's the dot product. Okay. Now notice also that the whole thing gets multiplied by this sign. Why? What that sign has done is it has forced the surface normal to flip sign if it was coming in. Okay, by assigning this minus sign here. So any surface normal that was actually pointing into the control volume, once I introduce that sign, automatically get flipped to the other side. So now I'm calculating the divergence with all the surface normals pointing outwards. Okay? If I did not have this guy, then what would happen is, you know, your signs are inconsistent. Sometimes you're looking at surface normal inwards, sometimes you're looking at surface normal outwards. Okay? Everybody understand that? So that's what this whole thing is doing, and this is how it's used in the end. Okay, let's talk a little bit about interpolation now. Now, when we did this nice structured Cartesian mesh, everything was so easy because whenever we wanted to calculate something at a face, we would just take the two cell centers and divide by 2. That's it. Okay. Now you cannot do that anymore. So this is what we had used for a Cartesian mesh. Okay. Now one could write it this way. Okay. So what we really have is a weight which is half in for both cells. Okay. So we could write it in general like that. A weighting function times the eastern value plus 1 minus the weighting function times naught. Okay. Now, how do we get those weighting functions in general? So suppose you have a mesh like that. Okay, so we would say gamma f is equal to this weight function times gamma 1 plus 1 minus the weight function times gamma 2. That's our formula for interpolation. Okay, so the question is, what is this weighting function? This weighting function is inverse distance weighted. So 1 over d1 is the inverse distance between those two. And then, so we are looking at the face center to the cell center. And 1 over d2 is the inverse weight or the inverse distance of d2. Why inverse? Because the influence of a cell dies as the distance increases. Okay, so it's not directly proportional, it's inversely proportional. Okay, so you can see here from this formula, let's say I make d1 very, very large compared to d2. Okay, if I do that, then that means 1 over d1 is very, very small compared to 1 over 2. Okay, and so what will happen here is your weight function is going to become, basically you can see here, this guy is going to be tiny, this guy is going to be tiny, so you're basically going to get almost 0 over 1 over d2. So the weight function will be 0. So in other words, d1 will have no influence, or gamma 1 will have no influence on that face value at all, because d1 is so far away. Okay, it will pretty much be equal to gamma 2 in the limit. All right, so that's distance weighted interpolation. Now, of course, one could do Taylor series expansions and derive the truncation errors associated with those kinds of interpolations, and it's easily doable for a Cartesian mesh. Again, difficult to do for a unstructured mesh. Okay, but typically, if you do this for a Cartesian mesh, this kind of a formula, you will find that it's delta x squared. Okay, as we've seen before. So now one other point I want to make is sometimes people, instead of using this, okay, they use a formula where they use distance square interpolation. So 1 over d1 square divided by 1 over d1 square plus 1 over d2 square. That's another method that people often use. And the reason they use that is it's kind of derived from physics. Okay, in physics we know that, you all know this, that when you have attractive and repulsive forces, they scale as the square of the inverse of the distance, 1 over r squared. Okay, whether you look at attractive forces between planets or two atoms, it goes as the inverse distance square. So that's the idea people often use. They say, well, it's the influence of something on something else is going to decay much more rapidly than just linearly. It's going to decay as the square. And so both have been used. This one is more popular. People tend to use this more, but there are cases where this has been used. Okay. Any questions? Okay, so this is done as this weight function calculation is done as a pre-processing step. So this is all still pre-processing. We're talking about the geometry and all that. Okay, so what do? You loop over all faces in your computational domain. You get the cell index 1 and the cell index 2. Those are the global cell indices from your connectivity information. See, this is where we are using the connectivity information that we already stored, face to cell connectivity. Okay, so you get cell 1, cell 2, the indices. From those indices you can get the coordinates, x, cell center, x, y, z, and then you also have the face centers, x, y, z. So we're simply calculating d1 and d2, two distances. All right, and then OD1 and OD2 are just the inverse, and then this is your weight function. So this is the weight function at a face. Okay. Now, how do we use it? Here is an example. This is the formula I showed you earlier. Once you have this and you've stored this, all you do is, if I asked you, okay, what is the value of gamma at a face? You just get the two cell center indices next to the face. That gives you gamma IC1 gamma at cell 1, gamma at cell 2. Those are the values that we have stored. We just multiply by the weight function. Okay. You don't want to do these kinds of calculations again and again. It's very computationally expensive. So you just do that once and store that information. Okay. And then you just use that whenever you want phase values. Any questions on that? Okay. Cell to vertex, same idea. We will see later on. Now, I should mention that all of these things that I'm talking about, you will see how that shows up in the finite volume formulation once we get to the actual equations. Okay. But vertex values will be needed at some point, not just for developing the finite volume formulation, but also for post-processing. Okay. Most post-processors want node-based data because they are designed for finite element type data. Okay, like TechPlot, if you look at, TechPlot will not accept cell-centered data. It will not plot it. Okay, it will want nodal data and finite element structure. If it's unstructured mesh. Okay, if it's structured mesh, then yes, it will take IJK ordered data. But if it's unstructured data, it will want it in finite element format with, the nodal values. So we need to calculate these nodal or vertex values from the cell center values. Okay, and the same thing is used here. We develop what's called a weight function for the vertices. Okay, same formula, inverse distance weighted. Okay. And once you have that, then all you do is to calculate the vertex value, you do phi I divided by di, summed over all the surrounding cells, okay, divided by the sum of the inverse distances, okay, and that becomes basically this guy. So once you have calculated and stored that, all you do is you just multiply that by the phi I of each surrounding cell and add it up. Okay. So that's your vertex value. Boundary faces are numbered separately in an unstructured code. Okay. And there are three important reasons for doing that. First, the boundary conditions are specified only on boundary faces, and therefore you need to store it only on those faces. If you try to store them on total face-based arrays, it's a huge waste. Okay, here is a little example. This geometry here has 71 faces, 22 boundary faces. Okay, by boundary faces I mean these guys, that one, that one, that one, and so on. Total faces also include, these, all these. When you refine the mesh, that ratio actually becomes much worse. Okay, you may have only maybe 5% of the faces may be boundary faces. Okay, so using total face-based arrays is a huge waste. You don't want to do that. That's reason number one. Reason number two is that this is related to computer science now. Okay, so here is how information is stored in a computer. It's stored in the form of one-dimensional chunks of data. Okay, so if you have, let's say, a total face-based array, it will go from here all the way up to here with gaps in between. Why? Because those gaps are for the interior faces where there is no boundary condition, nothing there. Okay, the boundary condition information are these red slots. Those have been filled with boundary condition information. But you've allocated memory for total number of faces. So it's a huge one-dimensional chunk of data with lots of gaps in them. Okay, so every time you want to get boundary condition information, what will happen is this pointer has to shift. So it will get that information, and then it will say, oh, now I have a gap, so I have to basically, it's called nullifying the pointer. It will nullify the pointer and then reset it up here. Okay, then it will get that chunk of data. Then it will nullify it again and then go here. Okay, it will keep switching the pointer from one point to another, which is quite time consuming for a computer to do. Okay, no matter what the architecture is, because you're not looking at a contiguous chunk of data anymore. All right. The way data is accessed from a computer typically in advanced codes is you just give it the starting location and the length of the data you want to access. Okay, so you give it, okay, I want the pointer hitting slot number 32, and then I want 1 million of the next numbers. Okay, it will get you 1 million of those numbers. All right. When it has to do this, it's problematic. If you do it boundary face-based storage, the entire data is contiguous. It's much smaller, first of all, and then it's in one chunk. Okay, so you set the pointer, it gets the entire boundary condition information of all the boundary faces in one shot, and you have it. That's it. Okay. So this is a computer science issue, but it dramatically affects speed of your computation. Another reason, if checks. Okay, so suppose I want to calculate the average of phi at the boundary. Okay, this is the example that I was talking about. You have a, let's say, a boundary, and you want to average the value of phi there. Okay, so if I use total face-based data structure, which is what I don't want to do, then what I would have to do is I have to have an if statement here which says check to see if it's a boundary face or not. Okay, before you add that value, and it'll do this check. Then if it's a boundary face, then it'll add it to the sum, and then after all of that you will go to calculate the average, saying okay, it's the total sum divided by the number of faces. Okay, but if you do boundary condition, so this loop is pretty large. Imagine you have 1 million faces. Okay, that's 1 million, and then you have to execute these if statements. And that's very, very expensive. This is one of the things I should, for all of you who write computer codes for your research or whatever purpose, something that's an absolute no-no. Do not use if statements within loops if you can avoid it. It's not a good idea. Okay. When we get to the finite volume formulation, I often see students saying, do I or for I going from 1 to n, and then they have these if statements within that saying, if I equal to 1, do this. If I equal to 5, do this. If I equal to 24, do this. Okay? No, you got to separate it out manually beforehand. Okay? Don't use if statements within the loop. It's extremely expensive. All right? So conditional statements are fine. If statements, I mean, the actual execution of the if statement is very cheap. But, what the computer does is it goes through what's called branch misdirections. So anytime you have a conditional statement like that, what the computer does is it takes both routes. Okay. So the if statement basically bifurcates the algorithm, right? So what it does is it processes both routes simultaneously. And then when the if statement is actually hit, it says, well, I can throw away this route. I'm going to go with this route. Okay. So part of the computation it actually did is wasted. So that's what happens in reality when it actually does the, when you look at the way the architecture handles these kinds of statements. So here is what we do to address this issue of numbering boundaries separately. Okay, so here I'm showing an example. The red ones are showing the global face numbers. The blue ones are showing the boundary face numbers. Okay, so we have a map that we store, which we are calling from link from face to boundary face. So for example, we're saying link from face to boundary face of face number 41 is 1. So what this is telling me is that global face number 41 is local face number 1. Okay, and the opposite, which is from boundary face to face, is storing the opposite information. Okay. One thing I should point out is the reason you can afford to store all this data is because most of it is integer storage. Okay, if you look at all the things that I've been talking about, store cell-to-face connectivity, face-to-cell connectivity, and all that stuff. This is all integer. Okay, integer storage is very cheap because, first of all, these integers are not going to be very large numbers. I mean, you're not going to have number of cells, number of faces which are 10 to the power 63 or something like that. So you don't need double precision integer storage. You need single precision integer storage which handles up to 10 to the power 15. Okay, which is plenty for number of cells or number of faces. All right. So all you need is single precision integer storage, which is 2 bytes. Okay, as opposed to storing double precision real numbers, which are 8 bytes. So considerably less compared to real number storage. Okay. So for interior faces, what we do, or what is generally done, is you store a negative number just to show that it's meaningless. Okay, that it is an interior face. So here is an example of where this kind of data structure is used. Suppose I want to compute the area weighted average of phi at a boundary. Okay. So what am I going to do? I'm going to run a loop over all the boundary faces. Okay. It's going up to NB faces. Again, notice that I'm not looping over all faces, just the boundary faces. Okay. Then what am I doing? I'm getting the global face index from the local face index using this data structure that I've created already. Okay. So I'm giving it the boundary face number. So for example, I would give it 5 and it would return 5 for me, this 5 from that. Okay. From that global number, I'm going to get the area, because the area is stored in all faces, not just boundary faces. So the area requires total number of face data structure. Okay. The phi at the boundary, though, is not something that has a total number of faces data structure. It's stored only at the boundary. So this index here uses the boundary face index. This index here uses the global face index. So area is using global face index. Phi at the boundary is using just boundary face index. It's mixing the two. Okay. Depending on what is needed where, because area is needed everywhere in my finite volume formulation, but boundary value is not needed everywhere. Okay. So you sum it up and then you take the average in the end. All right. Any questions on that? So that's a bit about boundary conditions. Notice that there are no logical checks. It's a much smaller loop. Okay. So next.